this. In continuation of the introduction to integration, we are still introducing ourselves to integration. These are the reversal of the differentiation we did initially. X raised to power n is going to give us x raised to power n plus 1 over n plus 1 plus c. 1 over x dx is going to give us ln x plus c. E raised to power x dx is going to give us e raised to power x plus c. E raised to power kx dx is going to give us e raised to power k x over k. You know, initially, if you had differentiated this, it's going to give e raised to power kx times k. So that's what happened here now. A raised to power x dx is going to give us a raised to power x over ln a plus c. You know, if you have differentiated a raised to power x, it will have given you a raised to power x multiplied by ln a, but now it's dividing it. Take note. Sin x dx is going to give you cos x plus c. Cos x dx is going to give you minus sin x plus c. Tan x dx is going to give you sec square x plus c. Sin x dx is going to give you cos x plus c. Cos x dx is going to give you sin x plus c. And then 1 over root of 1 minus x squared dx will give you arc sin x plus c. Minus 1 over root of 1 minus x squared dx will give you arc cos x plus c. 1 over 1 plus x squared dx, remember, it's going to give you arc tan x plus c. When you differentiate this, it will give you this. 1 over root of x squared plus 1 dx is going to give you arc sin x plus c. 1 over root of x squared minus 1 will give you arc cos x plus c. 1 over 1 minus x squared, if you compare to that of tan, arc tan, you can see, it will give you tan x plus c. So you can see, when you know the forward and the reversal, it makes your job very easy in this situation. You might not apply it every time, but there are some situations where you need to revert to this and then to make your work successful. Now, we have function of the linear function of x. Now, if z is a linear function of x, like ax plus b, in that form. So, if you have it like this, z raised to power n dx, we are going to make this dx to be in terms of dz. Do you understand? And then dz. I have one certain example like that in the previous one. Now, if you have another form like this, that is the differential of x is the numerator and fx is the denominator, we are going to have in fx plus c. This is applicable, or that's what we applied in partial fraction. We get it, partial fraction. So we got it from this. That is why we have the x, over x. That's what it's going to give us. Do you understand? Now look at this situation now. We have z raised to power n dz. That is, after you do all the abracadabra you can do, you come to a conclusion that what you have here is going to be dz. Like if you have an expression like this, a raised to power x plus b raised to power n, and you can still work out something like a dx outside. Are you getting it? Because dz of this is going to be a dx. At the end of the day, this is going to give you a raised to power x plus b raised to power n plus 1 over n plus 1. So just be alert, you can get to this. So you will not be terrified or be sweating out. What do I do? So look at this, look at this. They are very, very, very common. And by the time you work or practice, you get used to them. Now before we continue, I want us to do this and see how easy this can be. The first one is saying that we integrate 1 over 1 plus 4x squared dx. So if you look at this, it gives us something like this, 1 over 1 plus 2x squared. And if you look at this, it is differentiation of arc tan. So if you look at this, you can say 1 over 1 plus u squared. You can see 1 over 1 plus u squared. And then I can now say, yes. Looking at this, what is my u? My u is 2x. My u is 2x. My u is equal to 2x. So du is equal to 2dx. So dx is equal to du over 2. You can see. So I can now say this expression is now equal to 1 over 1 plus u squared du over 2. And this one is going to give me arc tan u over 2 plus. You can see that it makes the job very easy and straightforward. And what is my u? My u is 2x. So it's going to be arc tan 2x over 2. So I just want you to see how you put what you have, the result you have gathered to use. So we have another one. I equal to 3 raised to power 5x dx. So I You can see. So dx is equal to du over 5. Or you can write du dx is equal to 5. So it goes like that. Now, I can now make my substitution here. So this one will now be equal to 3u du over 5. You can see that it has made the job very easy. Now, you can also see 1 over 5, 3u raised to power u du. And you know, in our integration, what does this give us? 1 over 5 ln 3 over ln 3. So that is going to give us 1 over 5, 3 raised to power 5x over ln 3 plus c. So look at this. Breaking this one out makes the job very easy. You can see. It makes it straightforward. Now let's look at the third one. Now let's look at this one. We have 1 over 4x plus 3 dx. And this is a linear expression. Let's see how we can work it further. It's going to give us something like, okay, let's make it like this. 1 over u dx. I think we have our u like this. We can now say u equals to 4x plus 3. So du dx is equal to 4. So dx is equal to du over 4. That means I can write this as 1 over 4 into 1 du over u. And you know when we have it like this, it's going to give us ln u. So it's going to be equal to 1 over 4 ln u plus c. And what is our u? Our u is 4x plus 3. So it's going to be 1 over 4 ln 4x plus 3 plus. So you can see, it's very easy and fun. In introducing the topic, I laid down some standard results. I mentioned something close to this. That is, we can have situation of this one. And when we have it, how do we tackle it? I gave you the result. That is going to be ln fx. So, working on integration requires serious, observation. You have to observe to bring out your results. Looking at this, if you are not aware of these results, you might start thinking of, oh, how do I tackle it? How do I break it down? How do I do this or that? Or going to form to do some hard work, which is not necessary. So, by the time you look at this is part of the things you should quickly look out for. When you have an expression and you have the numerator and the denominator, quickly look at the numerator. Is it a differential of the denominator? If it is, it's going to give you a result like this. So you can see, this one is differential of this. Let's make this one u. So this one is going to be u du. You can see, that's what it is. So by the time you look at this, what does it give us? A u. Or in case it doesn't even come straight out like this, break it down. Make it, look at whatever you will need to do to make it the differential of the one below. Maybe you have to multiply it by a figure, maybe you have to divide it by a figure, or you have to break it apart. Just like it is done in partial fraction. Now let's look at what this one is going to be. If you have this one will give us, you can see, 2x plus 3. By the time you differentiate this one, it's going to be, so d dx x squared plus 3x minus 5 is 2x plus 3. So what does this one give us? Ln x squared plus 3x minus 5 plus c. That's how you do this one. Now, look at this one now. We have to integrate x over 3, x minus 3 over x squared minus 6x plus 2. Looking at this clearly, you will realize something. Let's quickly see. If we differentiate x squared minus 6x plus 2, our answer is going to be 2x minus 6. And looking at the expression above, you can see that this one is going to be 2 into x minus 3. Simple. So, we will now make it like this. Half into 2x minus 6 over x squared minus 6x plus 2. You can see, we have gotten a standard expression. And that gives us half ln x squared minus 6x plus 2. So sometimes this might be like something like 4x minus 12. So you know that we put 2 outside and then we do the needful. Very easy and very simple. Let's look at another standard we can have it, another form we can have it. Now, looking at the function like this, fx dx. What do you think this is going to give us? If we integrate, it's just like having, u du. That's just a simple way to explain it. So I look at this. This one is going to give us u squared over 2 plus. You see? So at the end of the day, this one is also going to give us fx squared examples. Now let's quickly have fun. For the first one, we have I integrating this time x square x dx. So if you look at it, this one is the differentiation of this. So we are going to have it like this: tan x d tan x tan x d tan x. You can see. So it's going to be tan x all squared over 2 plus c. Let me like that. So you can see what that one gives us. So for integration, you need ability to observe very well, and which you need to develop, which you develop over time with practice. If you don't practice, well, so this one is going to give us sin x d sin x. You can see because x dx is, if you differentiate this, so it's going to give us sin x over 2 plus. Straightforward. Now let's look at which other one. The x. Okay. So if you look at this, what does it give us? In x 1 over x dx. And if you differentiate the next, it will give you 1 over x. You can see. So you can easily write it like this: 1 over x. Okay, sorry. In x d in x. You can see. So it will give us in x all squared over 2 plus c. In x squared over 2 plus c. Now let's look at this one, the last one. X squared plus 7x minus 4 into 2x plus 7 dx. On observing, we see that this one is the differential of this. So we are going to have something like this: x squared plus 7x minus 4 d x squared plus 7x minus 4. You can see. So this one is going to give us x squared plus 7x minus 4 all squared over 2 plus c. I gave these examples just for you to know that you can easily apply this without fear. So thank you very much for joining us so far. Kindly follow, you need to follow, subscribe, share, comment, please, like. Let people know about this to encourage us. And I can assure you, we still have a lot to give. I appreciate you. Thank you very much. If you have any question, send it through you can even comment or send it through the other channel in the description.